I'm going to be taking you on a deep dive into Git. Git, of course, the very popular Git version control system. Can I see a show of hands? How many people are using Git? Maybe yeah, pretty much everybody, right? That's good. I'm glad, because this is not really, I've tried to structure this talk so that it makes sense, even if you've never used Git. But the fact of the matter is, you're here to learn about a version control system. And learning about a version control system that you're not interested in, or that you're not using, can be a little bit tedious. As my old boss used to say, it can be a little boring. The other nice thing about having used Git is that this is not really the best way to introduce the material, to introduce Git. My friend Emma Jane Hogben-Westby teaches Git, and she teaches people how to teach Git. And one of the things that is really off-putting to beginners is to start out and say, well, it's easy. It's just a directed acyclic graph. It really doesn't go over well. If you are, in fact, interested in learning Git or teaching Git to other people, I really recommend some of the stuff she's written and recorded. Okay. Real quick introduction about myself. Again, I'm a software engineer at GitHub. I write a lot about version control. I've been doing it for a painfully long time, and all that data is kind of accumulated in my head, and I want it out so I can make room for new memories, like what my wife looks like, or the future sons and daughters I'm going to have. So I write about it so you can follow me on various social medias. So why are you here? Why do you care about how Git works? I care about how Git works because that's what I do for a living. I take the bits out of your Git repository and put them on a hard drive in our data center. So it makes sense as to why I care about it. But why do you care about it? Why are you here? Well, if we rewind a little bit and we look at the genesis of Git, I'm sure a lot of you already know this. Git was written by a guy named Linus Torvalds. If that name sounds familiar, it's because he wrote the Linux kernel, and he actually wrote Git in order to help him build the Linux kernel. And when he did that, he set out 4 goals for the Git project. He wanted it to be fast. He wanted it to support a distributed workflow, because there are kernel hackers all over the world. He wanted some safeguards against accidental data corruption. And if at any point he needed to make a decision, an architectural decision, he would look to the CVS project, another version control system, as an example of what not to do. And that's very cute, and it's mostly accurate. But what's missing from this list is being easy to use. And in fact, Git is not easy to use, sort of famously so, at least internet famous. As soon as you've got an XKCD written about you, I guess you're internet famous, right? But the thing is, it's really true. Git has a lot of commands. Some of them have strange names. Sometimes one command does several different things, and it's not entirely clear why. And when you run those commands, you do, in fact, get strange error messages. My favorite is, oh, you're in a detached head state. How many people have been in a detached head state before? How many people knew what the hell it meant? Right, exactly. And when you want to learn about Git, when you want to understand these things, you go to the documentation, which is itself a little bit strange. The top one, forward port local commits to the updated upstream head. If you told me that a command was going to do that, I've written an implementation of this command. It's rebase, which is not a simple command, I'll grant you, but I don't know what that means. And so now a quick aside, my slides are liars. I'll tell you the truth, but my slides, they're lying to you. And I'll try to tell you when that's happening. Right now, one of these is not an actual excerpt from a Git command. It turns out that the Git man pages are so complicated that somebody has taken them all and stuffed them into a Markov chain text generator. And out pops the Git man page generator, which, if you've been struggling over the Git commands, you should maybe go check out. It's a lot of fun. In case you're curious, it's this third one. Reveal all downstream commits below the sent upstream paths. That's meaningless. But it's not that much more meaningless than anything else up here. So I think it's really important to understand how Git works kind of at a low level, because the commands seem really weird until you really understand the data model that they're attacking, because the commands are really just a leaky abstraction on top of the data storage. So if we want to start thinking about how Git works, I think the most important thing to do is really define what it means to be a distributed version control system. Because I think that's where architecturally most of Git's, well, architectural decisions come from. So again, open source developers, especially the Linux kernel developers, incredibly geographically distributed. And what you don't want on a team like that is a centralized version control system. You know, at the very least, if you want to query history, that means talking to the server. And that's annoying when you and your coworkers all work in an office and down the hall in a machine room is your version control server, right? But it's tenable. It's not tenable when everybody's spread out all over the world. You've got a version control server in San Francisco, and you're working in, I don't know, Europe, right? Some centralized version control systems, yeah, like Team Foundation Server, I'm looking at you, are really painful, and you have to be online to do anything, to find out what you've done locally, just to get the status of your working directory. You've got to be online. You want to start editing a file? Yeah, online. Absolutely not going to work for a distributed team. A distributed version control system doesn't require any server at all. Obviously, best practice still is to have one, you know, to have a single source of truth for your data. Maybe it's GitHub, maybe it's, I don't know, a file share in your basement, right? That'll pass. But it's not required architecturally. And what that means is that each user has a full copy of the repository, all of the history, all of the files. You do everything locally, even checking in your changes. And that's a really interesting change from a centralized version control system, when you start checking in your changes to your local repository. And then you figure out how to share them with your coworkers, right? You push them to a server. It's 1985, so you put them on a floppy disk and walk them over. It doesn't really matter, but the important point is that the committing to your local repository and then pushing are two separate steps in a DVCS. Okay? So the actual format of the Git repository is what enables this distributed workflow. Just to take a really simplistic example, let's say I'm working with my coworker Alice, and we both cloned a repository at some point in time, at the same point in time. So, you know, we've both got all these changes, commits 1, 2, and 3. If I make a change and check it in, I'll get change set 4. If Alice makes a change and checks it in, she'll get change set 5. Again, these are only on our local repositories. I actually have to get Alice's commit somehow. Maybe she uploads it to GitHub and I fetch it. And then these are still independent. You know, in a centralized version control system, I'd check in 4, Alice would come and check in 5, and our changes, the server would take care of, you know, arbitrating that and merging our changes together. In a distributed version control system, I actually have to do that myself, and I make a new commit 6, right? And if we actually take a look at how this looks on the system, we can see, okay? You know, usually when you run git log, or maybe you look at the history on GitHub or another hosting website, it's just a flat list of changes, very much like what you see in a centralized version control system. But if you run something a little bit more invasive, I use this a lot. This is the log command I use all the time. Log -- graph, -- one line, -- decorate. Then you actually see how history kind of diverges with my change on the left, Alice's change on the right, and then flows back together when I brought her change into mine and made a new commit, right? And of course, you can use graphical Git tools to do the same thing. I'm not using GitX because it crashes on me. Well, that's fun. Let's just look at the graph again. Yeah, I mean, this is the same thing I was looking at on my slides, just you know, just turned upwards, right? So, and this is the graph. You know, it's a directed acyclic graph. We call it a DAG, or simply the graph. I didn't super do well in graph theory in college, so bear with me. But it's directed in that each commit leads to another. This is another little lie. My arrows are going forwards, you know, 1 begat 2 begat 3. We'll see in a minute that actually the arrows should be pointing backwards, but it's really awkward to draw them that way. But in either way, that's sort of an implementation detail. The graph itself has direction, right? Commit 1 leads to commit 2, leads to commit 3, et cetera. Okay? And it's acyclic. What does that mean? Well, it means there are no cycles. Yes, that's not a very helpful description. What is a cycle? It means that we check in, commit 1, that leads to commit 2, then commit 3, and we can't have commit 1 depending on commit 3. And that makes sense too, right? There's sort of a time causality issue if we could do that, right? If we could commit change set 3 before change set 1, then, well, things are a little bit out of order, right? So it turns out I've kind of lied to you again here, right? And if you've used Git, like most of you have, you probably know this. There's no such thing as change set 1, right? Because there really couldn't be. When I go to commit my change and Alice goes to commit hers, how do we know which of us is 4 and which one of us is 5? Why aren't we both 4? Right. We need a server to arbitrate that to kind of tell us who gets what commit ID. And in fact, if we had a server, we wouldn't be a distributed version control system anymore, right? So it turns out that Git does something really clever. I think the Monotone project was the first version control system to do this. It takes a hash of the commit contents. And that hash, it uses SHA-1, which is a 160-bit hash. That turns out to 20 bytes. When you turn that into a hexadecimal string that we want to talk about instead of just binary gibberish, although it still looks a little gibberishy, but that's beside the point. You've got a 40-character long string of hex digits. So you get commit IDs like 47BF0C3, that sort of thing. We can usually talk about just the first 6 or 7 characters because that's all it needs to uniquely identify it in a Git repository, right? So that's actually how the commit IDs come about, right? We don't actually see 1, 2, 3. It's not subversion or CVS, okay? I said we take a hash of the contents of the commit. So what is a commit? Well, it's a snapshot of the repository at a particular state in time, okay? A lot of people think, and Git is very guilty about this, that we're storing diffs as a commit, right? If I check in one commit and then I make a change to a file and check in another, a lot of people think that, that Git will store a diff when that happens. And especially because if you run git show on a commit ID, it shows you a diff. If you, to look at what changed between 2 commits, you run the git diff command. But in fact, Git is not storing diffs. Git is storing snapshots at each point in time for every commit. And it's calculating those diffs that it shows you on the fly. You might think that this gets very expensive, disk-wise, right? We're storing a complete copy of the repository every time we do a commit. Well, we're not, in fact. And so it doesn't get too bad, because a commit is actually created from other objects called trees and blobs. Trees represent your directories. Blobs represent the files inside of those. And just like Git hashes the contents of a commit to produce a unique ID, Git hashes the trees and the blobs as well. And that means, as long as you're not changing the contents of a file, its hash isn't changing. And so it doesn't need to store another copy. It knows it's already got a copy of that file in the database. Okay? What does that actually look like? Well, let's say I have some commit that has one file in it. I've just got one file in my repository, file1.txt. That means I've got a commit object. I've got a tree object. The commit points to the tree that represents the root of our repository. If I had other files and other directories, I'd have more trees and more blobs here. But I don't. I just have this one, file1.txt. It's a blob, and it's got that hash. That's a hash of its contents. If I go to add another file, I don't have a duplication on this file1.txt blob, right? See, they're the same hash. I don't need to store a second copy in the database. All I need to do is store a copy of file 2. I do get a new tree since it points to both of those files. And then I get a new commit with that information. Let's take a look at what this actually looks like inside the repository. I'm going to take a look at this commit 3741305. Like I said, it is a little bit of a mouthful. Okay? So first, I'm just going to look inside my working directory, right? I've got a bunch of files, and then I've got this directory here called .git. Since it starts with a dot, it may show up as hidden unless you use the -a flagged ls. On Windows, it's actually got a hidden attribute, so you've got to go and unhide it if you want to go poking around in it. And I think you should. I think it's great to go poking around in your Git directory. Maybe don't change things, but I think, just, whoa, hey, repository corruption. And if you do, please don't email our lovely tech support because they won't be able to help you very much. I think reading the Git repository is just fine. So let's look at what's inside, right? I've got some files, I've got some folders. One of those folders, this is actually the Git database itself, right? When we say you've got a local copy of your repository, this is what we're talking about. This is where all the history lives. This is where all the files that you've ever checked in live. And the files themselves actually live in objects, the objects directory. Okay? And if we look in there, we see a bunch of 2-character hex strings. Well, so what Git is doing is it's actually fanning out the object storage so that not every single object you have is in a single directory. So if we wanted to look at our commit, which was 3741 something, then that's stored in the directory .git objects 37. And there it is. There's the rest of the ID, 41305. Okay? What does that file actually look like? Oh, well. That's not very helpful. It turns out that this is a zlib compressed file. All of the objects, when they're stored loosely like this, just straight on disk in the objects folder, are zlib compressed. Okay? Fortunately, Git gives us a little helper program to use. We can run git cat file commit. This is a plumbing command, if you're not familiar with it. Git splits up its commands into what are called porcelain commands and plumbing commands. The porcelain commands are the ones that you use all the time: git status, git commit, git add. And then the plumbing commands that you probably don't run yourself. Git itself invokes these programs to do things. So we can run git cat file commit. And all that does is it decompresses it and spits it to our standard out. Very straightforward. When we do that, this is actually a commit object. It's just plain text. And it's got a tree and a pointer to the tree ID. It's got a parent and a pointer to its parent. That's the commit that came before it. It's how it builds the graph. And it's got some metadata about who committed it. It was me and when, and a commit message. Very straightforward. We can do the same thing. We can run git cat file on a tree. And we can see the actual repository that we checked. Oh, no. Turns out trees are binary. That's just for a little efficiency when parsing them. Git gives us a different plumbing command, ls tree. And we can see exactly what is in the tree. I've got something that looks suspiciously like a Unix mode, but isn't exactly. And a list of the files that are in this directory. At this commit, I just had 2 files, file1.txt and file2.txt. If I'd had some subdirectories, I could have trees here. That's how we build up the data structure, the actual file system structure. Okay? And finally, I can look at one of these files. Again, I can go back to cat file blob because my blobs are just files. They're not binary data. I'm not checking binaries into Git, at least not without using git LFS. And neither should you, because since we keep a copy of every file that's been checked in like this, a lot of binaries means a big repository. So I'm just checking in text files here. This is file 1, right? And if I actually look at my file 1 on disk, you'll see that it's the same thing, right? So we've just checked in this binary, this text file as a blob right into the database, okay? Those are commits in a nutshell, and the Git object storage. Commits are great. It's sort of the first most important thing that you do in a version control system is to be able to commit to it. But commits are not like super useful all by themselves unless you can branch, right? Having commits means you have the ability to save your work. But branching is what really makes a version control system so powerful, because it means that you can have two parallel lines of development going on. That is to say that I can be working on a feature, maybe I'm halfway done with it, 10 commits in, it's taken me a couple of days, and I expect 10 more commits over a couple of days before I'm done. And a super important bug can crop up in production that I need to fix right away. With branches, I can put my feature work aside, go fix that bug, and continue on. If I didn't have that, I'd have to fix the bug and then deploy my half-baked feature branch to production with the bug fix. That's terrible. So branching is super important in a version control system. And in Git, it is very, very straightforward. We've already actually seen it, right? I did some work, Alice did some work. We both started at the same place, and our work happened independently, and we were able to commit it independently. So we were actually seeing branches there without actually calling it that yet. And that is really basically how branches work in Git. They exist at the repository level. This is unlike, say, Subversion or TFS, where you've got a trunk folder, and then you've got maybe a branches folder, and then a collection of branches inside the repository. In Git, you branch the entire repository. And they're exceptionally lightweight, because what we saw with that graph, a branch is a pointer into that graph. The other nice thing about branches is that they only exist locally on my local machine, like everything else in Git. They go to the local repository, and you have to explicitly share them. What that means is, if I'm even creating just a bug fix, I'm going to go ahead and spin up a new branch and start hacking, because I can throw it away if I don't want it. Nobody else has to see it. It encourages branching and experimentation. I think that's a good thing. What do I mean when I say it's a pointer to the graph? Well, hey, it just points to a node in the graph. And actually, that really is basically how it works. If I have a branch called mine, which is where I brought in Alice's change, and maybe I got that Alice branch right there, right? What does that look like on disk, though? When I say it's a pointer in the graph, what does that actually look like? Well, if we go back to our Git folder, next to objects, right below it, is the refs directory. And that's where Git stores your references. If that doesn't mean anything to you, so there are two types of references. There are tags, which are tags, very straightforward, and then there are heads. You'll see that other directory there. What's a head? Well, that's a branch. Sometimes Git has some confusing names for things, but your heads are your branches. And if we look inside that directory, I've got two. I've got two files there, Alice and mine. And those actually reflect the two branches, Alice and mine. And if I just dump the git refs heads mine file, I've just got a commit ID. So when I'm talking about the mine branch, it really is simply a pointer to that commit ID right there, right? Similarly, I've got an OID in Alice's file that reflects her commit ID, and I can, if I show what that commit ID is, if I actually type it correctly, then you'll see that it is actually just a pointer to that commit that Alice made. Okay? But what branch are we actually on? We often think of ourselves as being on a branch when we're working with version control. I said that I was on the mine branch. How is that determined? There's another kind of meta branch called head in all caps. And head is not a pointer to a commit, usually, like the other branches are. It's actually a pointer to a branch. Okay? And if I open up my Git repository, I'll see one of the first things listed is head in all caps. And if I look at that file, it says refs heads mine. Okay? And if I, and so again, if I look at refs heads mine, that's got an object ID in it. So head is really just a pointer that tells me what branch I'm on. If I switch branches by git checkout, if I git checkout Alice, that'll update the head file to point there. And of course, it also checks out all the changes, right? If I go back to mine, the interesting thing about being on a branch is that as we commit new things, we're still on that branch, right? That means our branch pointers must just be updated to point to that new commit. And indeed, that's exactly what happens. Let me create a new file. We're very excited about it. We'll put an exclamation mark in. We'll add it, put it in the Git database, and we'll commit it. Okay. I hope that you use better commit messages than I do, but I'm in a hurry. If I look back now at git head, of course, I'm still on the mine branch. And if I cat the mine file, we see that it now points to ff5fca, which is the commit that I just made. So the head branch stays the same, keeps pointing to mine. Every time we do a commit, we update the object ID in the branch that we're on. Okay? And so that's how we have the notion of being on a branch. Okay? Branches are great, but they're only great if you can actually merge them. Otherwise, you can either deploy your feature or you can deploy your bug fix. You can't deploy them both. Obviously, we want to be able to have our feature and our bug fix at the same time, and that's what merging does. And Git is really powerful at merging. Okay? If we look at our graph before we did the merge, right? I've got my commit, which is 47BF. Alice has hers. If we want to merge these, it's actually really quite straightforward. Okay? In some version control systems, any version control system that isn't built on a graph, that doesn't have a DAG as its underlying sort of data model, finding the common ancestor to do a three-way merge is kind of hard, right? So what happens is in, say, Subversion, when you create a branch, Subversion remembers where that branch was created from, and that's the common ancestor for any merge operation that takes place. Anytime you do a merge, it updates that common ancestor with the information. And so you can kind of imagine that trying to remember these things is really painful. Team Foundation Server takes this a step further in terms of pain. And you've got, if you have some branch, foo, and you branch bar, and from bar you branch baz, you can't you can't merge baz into foo because it doesn't actually keep the data about the ancestry. And so you have to do a baseless merge, which is barely a merge at all, and it's nothing but conflicts. It's terrible. Don't do baseless merges, okay? That aside, so how do you find common ancestors in Git? Well, it's right in the graph. We can, with a repository this simple, we can look and see, right? All you have to do is start walking from one of the heads of the branch, and then start walking from the other, and the first commit you see in common is your common ancestor. I mean, it's super straightforward here because this is very, set up for this exercise. But you can even look graphically at a more complicated repository and usually eyeball a common ancestor between two branches eventually. So we take the common ancestor and we take the changes that we've made. We basically diff, for all intents and purposes. We diff mine and the common ancestor, and we diff Alice and the common ancestor, and we put the blend of those changes together. Okay. It's very straightforward. We end up with a new commit ideally, that, that reflects both changes. And of course, we're on that, so we move the head and the mind pointer along. Okay? So if we reset ourselves back to before we merged anything, like I said, I run this command a lot. Actually, I run it so much that I never type it all out. I have an alias, git LOL. Git log dash dash graph dash dash one line dash dash decorate. It's great, I use it all the time. So if I run git LOL, I see that I've got my change. I don't have Alice's. As soon as I run git merge Alice, I'm asked for a commit message, and it's brought in. We saw this exactly before, right? My change is on the left, Alice's is on the right, and then we have the merged change. If we look, we see that we brought in her file, basically. Okay? I'm sure you've all done this. And I'm sure you've all seen something special that really only a version control system based on a DAG can do. And that's what's called a fast forward commit. Technically, a fast forward is when you are your own common ancestor. What does that mean? Well, again, we can see it's pretty straightforward here. I have a feature branch called feature, because I'm not really good at naming things. And I have a master branch here. If I want to try to find the common ancestor between these two things, I'm going to start walking from my feature branch back down the graph and start walking from my master graph, finding the first commit that they both have in common. And it turns out, oh, hey, I'm right there. It is my master branch. That means that there's no string of commits here leading off master. There's nothing in master that isn't in feature. So if I want to merge feature into master, I just update the pointers, right? I haven't lost any data, by just changing that pointer. There's nothing to lose. So I can just do a fast forward merge. And you've probably seen this if you've done a poll. Maybe if you are good about creating topic branches and you have a master that tracks your origin master, and you run git poll origin master from your master branch, you'll often see that you're doing fast forward merges. Okay? Just real quick, just to drive this home. If I go back to a time to commit 3, right? This was the change that both I had and Alice had before we started making changes. And if I run git merge Alice, you can disable this, of course, but by default, if I just run git merge Alice, it tells me I'm doing a fast forward. And it tells me the object ID, the commit ID that I fast forwarded to. And if I run git LOL, very straightforward. It just updated mine to point to Alice. Head, of course, stays pointing to mine. Why is that useful? Well, it keeps you from having additional cruft when you look at the graph. While we're talking about merge, we have to talk about the very contentious topic of what other ways can we integrate code together, and of course I mean rebasing. There is no more maligned feature in Git than rebasing, even though it's actually really quite straightforward. We'll not talk about rebase interactive because that's not straightforward. That's got a ton of options. But simply rebasing a commit is taking the changes that were introduced on a branch and just plucking them off that branch and moving it onto another branch. Okay? I say it's really straightforward, haha. But I think it actually helps to understand what's going on inside the repository when you're doing this. So let's take a look. Okay? Let's go back to this commit. Okay? I've made a change independent of Alice's change. And if I were to just rebase right now, my branch onto Alice's, what it would do is it would take that change and stick it on Alice's, and we'll see how. But I want to actually look at what's going on inside the repository at this time. So I'm going to create a file called alice.txt. That will guarantee a conflict, because that's the same file that she added. Okay? And if I run git rebase Alice now, what I'm saying is I want to take these now 2 commits that I've made, pluck them off my history, and reapply them on top of Alice's history. Okay? And it'll stop and give me very scary all caps messages about having a conflict. Okay? And of course, git, being git, dumps the conflicts into a file with a bunch of arrows in it, and you're on your own now, right, to fix it. Okay? But what's actually happened inside the repository when we do this? If we look inside the .git directory, we see a new folder that wasn't there before, between objects and refs. It's the rebase apply directory. Let's go take a look at that. Okay? There's a bunch of stuff in here. This is the state of the rebase, because rebase will do some work and then stop and throw you back to your shell, and you've got to continue. When you run git rebase continue, it uses all of this state to reload the world so it can keep going. Okay? But the really interesting things in this folder are 001 and 002. Let's take a look. Pardon me, 0001. It's a patch. So is 0002. They're both just patches that contain the conflicts, the contents of the files in each commit. 0001 is the first commit that's being rebased, 0002 is the second. I think you get the idea. So what actually happens when you run git rebase Alice, Git goes and finds that common ancestor, and it starts creating patch files. It creates a diff of the first commit we made, then the second commit we made, squirrels them away in this directory. It checks out Alice's branch, and then it starts applying these patches, and it stops if you hit a conflict. So it's actually really straightforward how rebase actually works. Rebase interactive, again, a little trickier because you can do things like, well, while you can reorder them, and while you're in the middle of things, you can just run arbitrary programs, because that sounds like a good idea. But rebase itself is really just cherry picking these patches onto a new branch. I make it sound a little easier than it is, because of course, once you start hitting conflicts, you tend to keep hitting conflicts. But I hope that seeing how a rebase actually works is a little bit more, helps you understand a little bit more how that works. Real quick, what happened to the commit that we rebased, right? We had 2 commits on our old branch. We moved them to a new branch. And of course, when we did that, we changed their IDs. We actually created new commits with new IDs. And that makes sense, right? Because they've changed their place in the graph. Inside a commit, you store a pointer to your parent. If all of a sudden you had a different parent, well, that means the actual contents, the text of that commit are now different. When you hash it, you get a different hash, thus you have a different commit ID, right? Well, so that's true. We still have those old commits kind of hanging out. And nothing is pointing to them now. There's no branch pointing to them. There's no other commits building history on top of them. Eventually, they'll get garbage collected away. Git will run an auto GC, and but in the meantime, they're just hanging out in your repository doing nothing. Why do we tell you not to force push? Well, aside from the fact that all of a sudden pointers are gone and now people's work is strange. What if people had been building off of these commits? Well, now you have 2 sort of very similar types of content in your repository, and you've got to resolve that one on your own. It's not the most fun. So this has been a super quick introduction. There's a lot more files in that .git directory, and this has been a very brief introduction. I hope you go and poke around inside the repository yourself. I think there's a lot of good learning to be had by looking inside the repository, not touching, just looking, and running the Git plumbing commands. I think that really elucidates how Git works as a version control system, and I think that will really kind of boost your Git usage. So thanks for coming out. I know it's late in the day, so appreciate it.